Okay, everybody, welcome back to day 2 of our Visualizing Ceramic Structures tutorial here through the American Ceramic Society. We're going to pick up a little bit where we left off, where we're going to do additional examples of felt refinement for part of today. I don't want to spend the whole day doing that. It's meant to be sort of an introduction to the topic. We can always follow up offline if you've got additional questions. But I do want to show you how to do multi-phase refinement for sure, and then a few other things like limiting your profile space. So if you need to cut out portions of the diffractogram and refine around them, a few things like that I will be showing you. But then we're going to pivot and we're going to talk about how to use the Vesta. Vesta is a really great software. So I'll go ahead and share my screen. Um, Before we get started on the rebuilt refinement, maybe I'll point out this link to get Vesta. So I'll put a link in the chat here if you want to follow that. You can Google Vesta, but it's not the first thing that comes up. You have to type in Vesta plus something like crystal structure or crystallography to find it, or just follow that link to this jp-minerals.org. Vesta is phenomenal. Just like we love GSAS because it is free and it is really good. The same thing, oops. Same thing can be said for Vesta. It is a free software which can be used to generate really great crystal structures. Somebody says, yeah, you can run it without installation to get around your company IT. Yeah, that's right. Because you download it as a folder. For example, like when you download, I'll show you what it looks like on my screen. Let me hop over to my desktop. You literally just download this folder, and then it's an app inside of this folder. So running it is there's no actual installation required, and it's great. There's, of course, commercial alternatives, which are also, they do really great things, but you pay a lot of money for them. So Crystal Maker is, I think, the most popular one, but I think there's a few others that I'm drawing a blank on the names of them. But in my opinion, Vesta is all you need. And I say that not just from my own opinion, but I guess also it sort of represents what I see at conferences where solid state chemists, material scientists, ceramicists are working. It is by far the most commonly used platform, and it's free to use, which is great. Okay, let's dive back into refinement, and then we'll go back to that. But like I said, if you want to be downloading your Vesta package, if you go to this Vesta page I just linked, and then you hit this download button right here on the left, if you click that, it will bring you to the options to download it for Windows, Mac, or Linux systems, and super easy to use. Okay, we'll come back to that in a moment. Okay, so the example I'd like to do today, since we talked about how to do a Lab 6 example, and the point of learning how to refine something like lanthanum hexaboride, it could have also been silicon or corundum, as long as those were standard materials. Remember, the whole point of doing that was to learn what the zero and the profile parameters should be for your material. Once you have those, we can use that same zero and those profile parameters as a starting point for when we refine actual materials, and it's going to make our life a lot better and more accurate. So now that we've done that first one, let's shift gears and let's do an example of this one. This is going to be 90 alumina, 10 silicon. So I actually had my students mix together some corundum, alumina, and some silicon by weight percent, 90 to 10. They grounded those powders together, packed them into an X-ray diffractometer, and they measured it. And we're going to look at that pattern and see if we can refine it and get anything close to 90-10. Okay, so to do that, we're going to follow the steps like before. So again, the first thing I always do, it's probably best to save it as a new project. And I like to put it, so we were working in the lanthanum hexaboride folder before. Now we're going to jump up here to the 90-10 silicon. I always like to make a second folder for where the actual refinement goes, because the refinement process creates a bunch of kind of junk files as it backs it up as it goes. So it's better just to put it somewhere where you don't care about those junk files existing. So I've got that created now. So now that we have that, I'm able to import my powder pattern and import my phases. So let's do the powder pattern first. We're going to go to import powder data, and I'm assuming it's a Bruker raw, but let's double check. It might actually be different on this one. I can't remember. So I go to my Rietveld where this is located on my computer. I've got my examples, my 9010. Okay, so okay, so it has a raw file. Let's try that one first. But I see that I've also got a couple other files, like an XY file and a BRML. So maybe the raw file didn't work, and that's why I had to go with an XY file. Let's check. So I'm going to come over here to my Rietveld refinement software, GSAS. I'm going to try to import powder data And let's try Bruker raw first. And there it is. And it says, okay, this is a binary file. Do you want to read it anyways? Yep. Okay, so it's giving an error. So I don't know what exactly was wrong with that, but it's not able to read it in. So this is where it's really useful to use that software POWDLL, right? POWDLL. And again, the whole thing that POWDLL does is it allows you to import files in all of these different formats and output them, export them into all of these formats. So the fact that looking in this folder, that I see that there's an XY file probably means that I tried it with this raw and for whatever reason it didn't work. And so I converted it to an XY file, which should just be a text file. We should be able to open that with like a notepad or something, and you should be able to see that it's just X and Y data, right? So there's your basic data like that. In other words, a lot of times these things, when you were to open them, let's try opening the raw file for a moment, see what it contains. We'll just try opening it with, there you go. Try and open this with Notepad and see what we see. Okay, see, check this out. So they're actually encoding the information differently. It's not an ASCII encoding, it's something else. And they usually do this because they have a proprietary file format and they don't want people to interoperate between them. Thankfully, somebody over here at PowDLL put in the hard work to figure out how to do those interoperations to make it easy to convert it over to data. But what we lose here is the header data that is commonly found that describes what instrument did the measurement, what were the optics that were used, what was the step size, what was the delay at each step, right? All that information has not been captured in this XY format, but at least we have the raw data, which we can use. Okay, so now that we know that, let's come over here to our import and we're gonna bring in our powder data and we're gonna bring it in as, where is it? Let's see. Not civ, not dat, XML. Okay, right here. From comma tab semicolon separated file, but that would do it because we have a space separated data, or it might be a tab delimited. So let's try bringing that in using this XY data and see if that works. It says this is what it's going to look like. Do you want to read it in? Yeah, that's right. Okay, just like before, it's asking, do you want to choose an instrument parameter file or cancel for default? Again, I don't know what instrument was used to generate this data. I don't have the standard that was run on this exact one. So we're just going to go to cancel and just use a default one, assuming that it was copper K alpha data. We'll be able to check whether it was copper K alpha as opposed to one of these other sources that are available in just a moment. But since I've run through this one before, I know that copper is going to work. But I'll show you if we didn't know that, how we would be able to check it. So once we add this powder file, that allows us to do all of these things. We're able to look at the background, the instrument parameters, right? Again, had we already run a standard, we would now replace the 0 value from the default 0 setting to an actual value, which we got from our refinement. Oh, question about XRD giving volume percent was weight percent. It actually gives weight percent. That's a really good question. It's because if we go back to our SMZ method, it uses the molecular weight of the formula, and the formula is per unit cell, so it actually comes out to a weight percent. Good question, though. Okay, so we've brought in our powder data for this mixture of 90-10 silicon. Let's go ahead and import our phases now. So there's lots of different ways that we can import it. Last time we did it from sieve cards. Let's see what we have available to us this time. If I look in here, I see 1, 2 sieve cards. One is for alumina, one is for silicon. Great, so we're gonna bring those in. You have to do them one at a time. Now, right now, you might be wondering, where did you get these sieve files from and where will I get mine from when I wanna do this? That's a great segue for some of the other things we'll be talking about today when we talk about Vesta. There are a couple different databases to be aware of. Here's one. I'm going to drop a link into the chat for this one. This is the Crystallography Open Database. It is a pretty great resource. It's not perfect, but it's pretty great. It's very large, but it is not very well curated. So this has lots of junk data in it, unfortunately, but it's also free. So you kind of get what you pay for. You can use this website to download sieve cards for all sorts of structures. If you don't want something that it possibly has erroneous data, there's lots of paid versions as well, right? ICDD has their PDF4 and 4 plus, whatever databases that you can pay for. No, I guess now they're up to 5 pluses, right? They've got these things which are really great. They've got a PDF4 for minerals. These are really great. They've actually hired experts to go through and really curate them, to throw out structures that are probably nonsense, that were badly refined. And you very much get what you pay for here. These are awesome. Another really good one is the ICSD from Phys Karlsruhe. I'll drop both of these links in the chat just so you've got access to them. If I can remind how, there it is. These can be quite expensive, even for an academic lab where they give you, academic pricing. It still is going to be several thousand per year for a single license. I think ICSD, the last time I paid for it, was over 5,000 for their web access license. And that's just for 1 year. ICDD, I think, is a little bit more, but you can look into the prices if you're interested. I'm sure that you can get a quote for their products. If you wanted to learn about, say, the PDF5 plus database, you can reach out to them. It might say exactly how much. No, it's usually get a quote, because I think they charge different amounts based off of who's asking. And then the last one that I personally use right now is the Pearson database, the Pearson crystal structure database. I'm a big fan of it. I just think it's easy to use and it's about as good as any of the others. But those are all options. But today, since I'm not going to assume that anybody has access to these, we're just going to use the crystallographic open database, because honestly, you can use it most of the time with a lot of success. So in our folders, we already have the alumina and silicon files. But if you didn't have those, here's how you'd go about looking for them. In this COD, right, from the landing page, you're going to want to come down here to search. And then search gives you all these different ways that you can search for things. Like if you look at the top, maybe you actually know the ID number ahead of time, maybe, right? Or maybe you want to search by text or by what journal, or maybe there was like a key word that showed up, like a mineral name or stuff. It allows you to search up there. But by far the most common way that I search for things is right here using the elements. So we're looking for silicon, and it's just pure silicon. So I'm just going to put one element there. And then if I run it right now, if I hit send, what it's going to do is it's going to return any compound that contains silicon, but it might contain also other stuff. Like in this case, calcium, magnesium, oxide, silicon, right? That's an awesome ceramic material, right? But we don't want that. We want just silicon. So how do you make it just silicon? The way that you do that is right here in this box where it says number of distinct elements, minimum and maximum. We want one distinct element and no more than one distinct element. Okay, so now when I search, that's only going to return silicon. And what's great about this is it's going to return many structures, right? There's going to be many times that people have refined silicon, and you want to pay attention to make sure that you're getting it under the conditions that are relevant to your study. For example, they will often measure things at different temperatures, like right here. I'm looking at that example part of the way down. It says, okay, this comes from whatever, that second edition of Inner Science Publishers, but it was done at a high temperature. So somebody did a high temperature diffraction study where the lattice parameter is going to be larger than normal because it was collected at a high temperature, right? Normal room temperature right here, that's not right because those are the same size. So something's up there. But you will notice different sizes, which might be due to temperature, or this one was done at a high pressure, so that might have changed it to a different structure. The structure types are going to be denoted by the space group. The most common, so silicon we know is diamond cubic, which is FD3 bar M. There's two different starting points where you can put the origin, setting 1 and setting 2. I think that's whether it's at the corner or whether it's at the quarter position is the difference between position 1 and position 2 starting. They're symmetric structures either way, but there's just two different notations for how you define it. But you can see that the lattice parameters do change a little bit. Like this one's 5.381, this one's 5.427, this one's 5.43. So they're all close, but they're not the exact same. What we're going to hope is that by today using one of these structures, that it's close enough. So you would hit this button right here to download the sieve, and then you could use that. It says, hey, this is coming from an insecure website. Turns out crystallography.net is not secure. So we're going to have to tell it, yeah, it's safe, we trust it. And then you got that downloaded. You would do the same thing for alumina. We come back over here. This time I'm going to punch in Al and O. And this time I want it to have at least 2 elements and no more than 2 elements. So now it's going to return all aluminum oxides. And when we look here, again, the correct space group for corundum is this one here, this R bar 3CH, but there are going to be a few oddball ones. So it's helpful if you know what you're looking for ahead of time, like maybe in a paper or something you knew, like for example, if I just put like Al2O3 structure, I think even like the wiki page will probably tell us that it's corundum. Let's find it. Right, here's aluminum oxide. Let's see if it tells us the structure. Oftentimes these are pretty good. Yeah, right here. So it's telling us that that should be the space group, this R bar 3C, number 167. So that's how we would know to pick that one as opposed to one of these other goofy ones, which were maybe something that's metastable, maybe it was done at a high temperature or high pressure. Looking at the title of the paper sometimes makes that clear. The other databases have better metadata, like they do a better job of telling you that this was done at high temperature or whatever else. You also want to look closely to see what, sometimes they'll tell you in the title what information or what diffraction method was used. Like here it says an X-ray powder diffraction method, but it also says that it was done using NMR and TEM. So this could have been derived via NMR. Sometimes it'll say neutron diffraction or synchrotron. Those will give you a good idea of which ones are going to be higher quality. There's always best to go with synchrotron diffraction data for sure. Anyways, so that's how we can get our two structures. That's probably how I got these ones, okay? Either way, we have access to two structures, so let's try them out. I'm gonna come over here and I'm gonna import phase one at a time from sieve card, and I'm gonna grab alumina first. It says, yep, that's the one. We can rename it if we want, let's just leave it. We have to associate it with our diffraction pattern, so we're gonna click that box and hit okay, and then we're going to import one more phase from sieve card. This time we're going to grab silicon. That's a fine name associated with that pattern. Okay, so we're good to go. We now have our background information and we have information for each phase there. So just like before, nothing starts out selected for refinement except for our background. So let's go ahead and run that just to get it started. Before I do that, remember I usually go from 3 cycles of least squares refinement up to 10 because 3 is just not very many. I think 10 is a pretty safe bet to do. We're going to run this. It's going to resolve really quickly because we don't have very many parameters. It's not going to have a very good fit at first because we haven't turned on anything yet. We can take a look. Yeah, our weighted residuals clear up at 59%. It's not very good. Let's take a look at the pattern that's actually generating. Okay, so here's our pattern. We can look, just like before, we can zoom in and see where our error is at. Like if I zoom in on this one, it has a predicted peak in roughly the right position. So that means our lattice parameter on those sieve cards were pretty close because it's at least kind of in the right position, but it's way under reporting the value. Let's look at another one. Let's look at this phase right here. Looks like it's quite a bit over reporting that value. So it's over calculating. Now, we don't at first know what phases these different peaks belong to. Like it might stand to reason if this one's way under and that one's way over, maybe this one's alumina and that one's silicon or vice versa. And just the weight fraction has not yet been refined correctly, right? I'm pretty sure that's what's going on here. But if you wanted to be sure, one thing you could do is back on your home screen, remember this, if you, I think you have to unclick that button, the magnifying glass one down here, and you click this K one, that reminds you of all the different things that we've got that we can toggle. If you hit the A button, I thought it was A, you have to have that toggled. Remind myself how to do this. Let's see. Let me. Yeah, because hitting G should turn the grid on. It's not. Me see what's going on here. Let's try and refine it one more time just to reset it. So the background looks pretty good. Let's turn on one thing. So on our instrument parameters, we're going to leave all this alone for right now. It's eventually what we're going to want to change. Let's come down to our alumina and our silicon. Normally you would turn on the refine unit cells as one of the early things that you can change. So we can go ahead and turn that on for both of them. But more importantly, under this data tab, right? So for each phase, there's all these sub tabs like atoms and all this stuff. Under the data tab, we're going to click this button right here for phase fraction. Right now, the default value for the phase fraction is set to 1, meaning it's assuming that there is 1 unit of that phase present. And under Illumina, if we go to its data, it's also set to 1. In other words, by default, it's constraining them to have the same amount of each phases present. But we know that there's actually 90 weight percent and 10 weight percent. So by clicking that button, that allows us to refine the amount of each phase separately. If you do that, then you must come over here to your sample parameters, and you have to turn off your histogram scale factor. So what the histogram scale factor does is it takes your calculated pattern and overall it increases it up or down by some scale factor. But what we decided to do with the individual phases was to turn up and down the scale factor of individual phases. If you have both of those turned on, I'm pretty sure it will give you an error, and we can try it real quick. I think it'll say like, hey, these are correlated, you can't do that. So let's try and run it. Yeah, so it says you are refining a scale factor and all phase fractions for your histograms. This isn't recommended. It will be an unstable refinement, right? Because those are two correlated variables. So we're just going to cancel that and stop. Be like, oh yeah, right, we don't do that. I'm going to turn off my histogram scale factor. And now we're going to try and run it again. And we'll see if we get some improvement. Okay, way better. Okay, and now the legend is doing what I expected it to do. On this one, it disappeared. Let's see if I can get that to come back. Okay, over here, if I hit A, there it goes. So if I typed the A button when I collected this, this is what I wanted to show you was this legend. This legend is really great. First off, it shows you the plus signs, it shows you the calculated, the background, and the difference. But then these two ones, the blue tick marks and the red tick marks, show you which peaks come from which phase, which is super helpful. So again, now if I zoom in, say on these first two peaks, you can see like, oh, one is coming from Illumina and one is coming from silicon. You could have maybe Googled this on your own. Like this would be like the bad way to do it. You could be like silicon XRD pattern copper K alpha, right? And maybe because copper K alpha is super common, you could look here and you'd be like, well, what have other people done? You try and find silicon. And if you looked for long enough, maybe you could find a good pattern and then try and match it. That's not the best way to do it. Instead, we're going to show you how to do it in Vesta in just a moment, how to calculate. It'll just show you what the predicted pattern would be. Maybe I can just do that right now. So I'm gonna go to my Vesta. And in Vesta folder, if you've got it downloaded, I'll scroll down to the app. It's the one that has the application type here. I'm going to double click it to open it. And I'm going to bring in that file for silicon or Illumina, right? So I'm just going to open and I'm going to navigate to where I've been working, which for me is inside this folder right here. And we can open either one of these. Let's say that one, Illumina. So it's going to bring in the structure. More on how to do this later. I'll describe how do we use Vesta later. But for right now, really quick, I just want to show you utilities. And then you can go to powder diffraction pattern. So using this powder diffraction pattern, you can calculate it under all sorts of conditions, like if you have copper K alpha radiation, right, which right now that's what these are. These are copper sources. You can see either in a plot that the first peak is expected at, just like before, I can hover over this and down here at the bottom over here, if you pay attention to the X value, it's at 25.55. And we're seeing the same thing right over here at 25.57, right? So that's how you could have known ahead of time that that was the right, that's Illumina versus silicon, okay? So we will come back and talk a lot more about how to use Vesta in a moment, but that's one quick way to test whether or not you're seeing something where you might expect it. A better way would be to use search and match software, which will identify the peak locations and then do a matching algorithm to figure out which phases they correspond to. But there's no good free versions of that. The best free one is called Match. Which comes from Crystal Impact. So this does the same thing that I just described. Let's see if they have a diagram, but it's that sort of XRD peak matching where it looks like, yeah, it looks like this. This is actually a match right here, right? Where you actually generate something and it will try and show you which phases match it. but you kind of get what you pay for. I've used Match, and I just don't know if it's that good. It's okay if you pay for databases to populate it with, but if you use the default databases or like the crystallographic open database, it's just okay. In any case, we now have the ability to refine two phases independently. So at this point, we'd go back and we, just like before, we'd start to minimize our overall error. So you start to ask yourself, like, where is your error coming from? So look at some of the most intense peaks and zoom in on them and see what's going on. It looks like our peak shape is not exactly correct, right? It's too sharp from the actual peak, which is significantly broader. If we look at the really low angle peaks, that's where you typically see the most asymmetry on the left-hand side. And yeah, there's a little bit of asymmetry there. It's not too bad. Let's compare that to the high angle peaks. High angle peaks are being over-reported. Our intensities are too high. Again, we are too sharp. It needs to be broadened, and the values are too high. The values on these low angle peaks are too low a little bit. So that's usually a thermal displacement problem when you see that systematic shift where it's too high and then too low, or too low and then too high. But clearly the biggest thing we can do to improve this is going to be to improve our instrument parameters. By the way, just by adding, look how much better it got. It went from 59 clear down to 42. We had almost, whatever that 17% improvement. That's pretty big just by turning on independent phases. We're going to do a lot better as we turn on instrument parameters. I wish we knew what the zero was for this, that we had a standard for it, but since we don't, we're just going to leave it at 0. If you turn it on, I bet it gives us an error, because if we have our 0 refinement turned on and we have one of these lattice parameters right here turned on, those are correlated features. So if we run it, it should give us an error, I would think. No, it's going to do it anyways. But you definitely shouldn't do that because those are correlated features. So let's come back up here to our instrument and set that back to 0. And let's try instead turning on one of our shape parameters, which is going to change the shape of this thing. U is the most important one. It's going to change it the most. So let's go ahead and run it with U. Okay, see those errors? You can see it in real time over here on the plot, just plummeting as it was getting much, much better. Let's see what our squared came down to, our weighted residual came down to. So we went down from, yeah, dramatic improvement, 59 to 42. Then we had a wasted run where we had things correlated turned on. But then when we did our shape parameter, it really took a big jump down. And let's take a look at how it's looking now. So again, just like before, I like to zoom in one by one of the peaks and see, like, yeah, it's getting better. It's too Gaussian and it's not Lorentzian enough, right? It's still got these big tails on the sides, it looks to me. So the shape isn't quite right, and it might not get right if we don't turn on Lorentzian. Maybe. It's not quite looking amazing yet, but it's a step in the right direction. So let's modify our shape parameters a little bit more. Let's try turning on some of these other instrument parameters. Let's do W. I'm going to turn off U for a moment. Look at it. Still not quite right. Let's try doing both of them at the same time. No, it's not really quite getting them. So let's try turning on LX. If you want to be safe, you can turn them on one at a time. I'm going to risk it and just try all three at once. This is going to add that, see that Lorentzian shape? It really added these tails, which improves it quite a bit. I think we're still seeing problems coming from having the wrong thermal displacement values, because I think we're still seeing, let's zoom out and see it. Yeah, we are, well, it's actually not too bad. Like normally if you zoom in on just the error and you see a systematic shift from positive to negative, which we still kind of are, this still tells me I think that we have a thermal displacement parameter problem where they're not correctly set yet. But it's getting better. If we come to our most intense peak where most of our error is coming from, it's just not the right shape yet. It's not intense enough. So let's try and modify our thermal displacement parameters over here. Again, whenever you're doing thermal displacement parameters on powder diffraction data, I think that you can adjust them to get a better refinement, but I think that there's a very good chance that they will refine to unrealistic values. Well, for one thing, they're already set at unrealistic values. The thermal displacement values here coming from wherever this card came from were just set to the same value and relatively low values. So that's not very realistic. They're probably not. And if you want to feel for what would be realistic, you could download a bunch of these different cards and just see what they have for their thermal displacement parameters. Like if we download that one, I think we already did. Let's download it again. And then we open that. Let's open it in just, we're going to open it just as a text file. And you can scroll down here and see what they use for their thermal displacement parameters. It's going to be down here. So it's telling us that it's oxygen, it's 2 minus, 18 and 12E. These are the Wyckoff numbers. More on that in a moment when we get into it. Here it's showing their XYZ positions. XYZ, that's their occupancy. And yeah, they basically just have 0 set for their thermal. So they never refined their thermal displacement parameters right there. So you could check a few others of these. Maybe you'd get lucky and you'd find one that has it refined. More recent, if you look at the date of when these were published, more recent ones are going to do better at it. Again, other software would let you rank it by date. Here, I don't see that option. We'll just look at one of these other ones from 94 real quick. Try one more. Open it. We'll scroll down to the bottom. And again, it doesn't have the thermal displacement parameters refined. So anyways, what this is telling me by looking at, seeing that these are both set to 0.01, is that they probably weren't actual values. Those were dummy values put in, and they're probably incorrect. So let's try refining our U values for this. While we're at it, let's take a look and see what silicon has for its values. Maybe it's worth turning those on as well. Again, they may refine to unrealistic values, but they will give us better fits. Normally, you want to be really careful if you do that, because the software, all it is just a fitting software. It's a curve fitting software. You can turn on all sorts of things to make it fit, but if it refines to unrealistic values, that's a pretty big red flag that maybe what you did is not actually telling you anything useful here. Here, let's take a look what they refined to. This is a normal value, alumina. Yeah, these are also like fairly, like they didn't go negative or anything. So that's pretty good. Let's take a look at what the pattern did. Way, way better, right? The intensities are much more close to matching. What was our value that it got down to? Oh yeah, see it plummeted. It's now down at 14%. It's approaching good enough for publication, right? We're getting pretty close to a reasonable fit here. We can start to zoom in and see what's going wrong. So it's going down and then up and then down again. So there's still a slight problem here, but it doesn't look like a symmetry problem, which I thought we were going to have to turn on. I didn't think it would be huge, but I thought we'd have a little symmetry one. This one has a little more of an asymmetry. It's going up and then just down the error curve. I think mostly we can just massage this with the shape parameters, the instrument parameters to describe the shape of the curve. Let's try turning on Y. Right, that is also a Lorentzian parameter, which allows us to slightly adjust things. By the way, if it's already pretty good and you're worried about turning things on that it might break it, you could always come up to controls and you could reduce the change. Oh, it's already set at the, hold up. Where's our, I thought it was right here. Maybe it was that. Maybe it's already at the lowest change. So it's making small steps at a time. Let's try running it. Might be getting a little better. Take a look at our notebook. And we're at, yeah, it came down to 13.5. So we still have some bugs to work out. There's a few things we haven't tried turning on yet. For example, where's our pattern? The powdered pattern disappeared for a moment, but when I clicked this one in the data tree, it made it appear. You kind of get what you pay for with this. It is free software. There are a few bugs like that, which are not quite spot on, but still, it's great software, even with the small bugs it has. So if we look at this, it's still getting some things wrong. Like this silicon phase is just like not nearly the right shape for the silicon phase. Something that might be happening here is we are refining one shape parameter for both phases. So, right, these instrument parameters, you're doing it for both phases, but you might have a scenario where one of your phases had a very different morphology that caused broadening, for example. Maybe it was like nanosilicon mixed with coarse-grained aluminum, in which case it would make sense that the silicon is much more coarse than the alumina. In this case, maybe it's the opposite. Like here is our alumina and our silicon together. It's fitting the alumina really well, but it's not sharp enough for the silicon. So it might be the case that the alumina was more fine grained and the silicon was coarser, right? That's something that's not being done. I believe it's possible to refine the shape of each phase independently, but I don't remember how to do that. But I think that that is technically possible, but that could be it. Or there could be something else going on. For example, we haven't yet refined the X positions of where these atoms actually are located. We could try and turn those on. I'm always a little hesitant to do that if you don't have really high quality data. And I don't like, look at this. Our intensity, our signal to noise ratio is not really amazing. 5,000 down to, it's not like it's amazingly good, but we can try it and see what happens. We'll try and turn on our positions. Maybe that will make a modest improvement as we refine the exact position of those atoms. Yeah, it's not a big improvement. I think it dropped down to 13.3. But we're getting close to about as good as we can do on this one because, again, the software as a refinement software, you just keep on clicking boxes and it will just happily keep on changing things. But at some point, you're changing stuff that isn't physical and isn't meaningful. And we're already getting pretty close to what would be an acceptable value anyways. So at this point, maybe it's worth checking how close did we get? We thought it was going to be a 90-10 mixture, and what is it actually coming out to? So here's our alumina. It's showing that it's 96%, and our silicon is 3%, right? So it was 97 and 3. So we're off by a little bit, but remember, about as good as you can expect with lab X-ray is plus or minus about 5%. So we're sort of within the bounds of it, and we know why the silicon is being underreported. If you come over here to your powder pattern, and we look at the two different phases of interest, right? Let me turn on my legend. Huh. Funny that's not automatically doing that. No. Either way, we know that first peak is corundum and the second one is silicon. And the silicon calculated pattern is not high enough. It should be higher if it's capturing that. So we know it's underreporting the value by a little bit. And that's coming out in the analysis there. Okay. Any questions people have about this before we move on to another one? Oh, I've not been looking at the chat. Okay, let me go through some of these questions in the chat. So this person said that they couldn't import the raw file. Yeah, so I had to switch when we brought in the file. Instead of using the raw, I had to bring it in as the XY using a comma separated value. Somebody said they could not open .txt. Which txt was that? Was that going back to the data we looked at? It wasn't any of these, so I don't know which one that was in reference to. You can type that in.
It was a Rigaku.
It was a Rigaku, that as opposed to a Bruker.
Yes.
Okay, so when we come over here to our data tree, there's the option to import powder data. So there's Bruker and it's got Rigaku TXT. I see. So having trouble opening that. If it's not working, I would recommend to use PowDLL and convert from the Rigaku TXT to something like a raw file is what I usually go to, or you could go straight to just the comma separated value if you'd like. Somebody else says, it would seem to me that for mixtures, you would always want to turn off the histogram. Yes, that's right. Anytime you're doing something multi-phase, you turn off the histogram scale factor, because again, that just changes everything up and down. And instead what we want to do is we want to turn individual phases up and down. Is match accurate? It is as accurate as the database that it is using. So again, this match software, it's pretty cool that it's freely available, and it's just the problem is that, so right here it says like download reference patterns calculator from the COD free of charge. So it uses the crystallographic open database as its default setting, and this is just it's full of a lot of junk. So when you actually use this to match patterns, it pulls up all sorts of supposed matches that are not matches at all, right? So match XRD peak matching. When you look at it, first off, it doesn't do an amazing job of finding the peaks. I wish it had some better job of finding the peaks. So it will have this pre-built-in search function that will take your data and identify that that's a peak, but it also thinks that's a peak. Like see this dashed line, it's not sure if that's like a shoulder, if that's a secondary phase, it thinks it's probably a peak. That's probably not. That's probably like K alpha 1 and K alpha 2 or something. But then when it tries to match it, it goes a little crazy and suggesting matches that are just not realistic. It does have some benefits, right? It allows you to like go through the periodic table and turn on and off different things. Like here's an example of one where again, here's the pattern. Forgive the grainy quality here, but it had a bunch of peaches. And then you can, over here in this periodic table, you can click which elements you think are present in it. And it's sort of just okay. If you have nothing else, you should definitely learn to use it as a starting point. But I've found, I've used other software like Topaz or Expert High Score, and they are excellent. They do a much better job of identifying candidates, but they also cost a ton of money. Expert High Score, even for an academic license, I think was costing us 20 grand a year for our department to have it. So very expensive, whereas Match is free and with a little bit of effort, it'll do the job. Where can we access the recorded videos? So those are the ones that Greg is recording for this. He can tell you. I have other ones on YouTube that I've posted, but he can direct you to the ones from this. Oh, in fact, he's got them right here.
Yeah, I sent it out this morning.
Okay. Somebody asked if we get lower values for the default values of U, W, X, Y, and Z, but still positive values, are those still physically possible or physically realistic? Okay, so for the U, W, X, Y, and Z, those ones don't have constraints about realistic nature for being positive or negative that I'm aware of. The thermal displacement parameters shouldn't be negative because that doesn't make sense for it to have a negative, vibrational space. But the U, W, X, Y, Z, I don't know. Those aren't based off of physics. They're just parameters in an equation that looks sort of like a peak. So they're not based in anything physical anyways. So I don't know what values would be unacceptable. I just allow them to refine to anything. Okay. And then he says, you're okay getting negative value for W. Is that still okay? Yeah. Yeah. I don't have a problem with that. These are good questions. Are there other questions I can answer before we move on? And feel free to interrupt me while I'm going if I don't, if that makes sense, so we don't get too far past what you were wondering about. So let's say that we wanted to try and refine this better, and we think that maybe, size or strain is causing the difference between these. One thing we can do is we can actually turn on strain and size right here. Like let's turn on size for a moment. We're going to click that for this. Let's make this smaller so it doesn't take over that. So if we turn these things on independently for size, if in fact the difference in the reason why we can't fit these is because one is a much smaller grain than the other, maybe this would fix it. That's a hypothesis, but we can try that. Let's try turning on individual size. That's going to change the sharpness of the peaks for the two different phases independently. And it looks like it improved it a little bit. It went down from 13 and a half or so where we were down to 13.1 maybe. A slight improvement. If we look at it, I'm curious what actually did to the diffraction pattern. Notice again that the powder pattern here has disappeared. To make it come back, I'm going to click this powder one in the tree, which will make it come back. And let's zoom in on those first two, which have been causing the problems. And just kind of not really made it better. It's really, the problem is that our silicon just needs to be sharper, but this one is already at the appropriate sharpness. So these two phases are just diffracting very differently. Okay. I still think it's a size issue, but I wouldn't know for sure what else to try. All right. Other question I see, do you single click or double click to come back? On this profile, if you want to go back, I don't think double clicking will do it because you can just keep on zooming in. It'll just zoom in to some arbitrary limit maybe. To go back, I'm hitting this home button at the bottom. And you have to actually hit the magnifying glass. If I try and like draw this, it doesn't actually work until I hit this magnifying glass. And then it will allow me to zoom in on different regions and look at them. But that's about it. Like the main things that we're looking for here is like, are there any peaks that aren't being captured? No, like they're all accounted for by one phase or the other, right? Even the little guys, little ones and big ones are all being accounted for. So it's not that there's a third phase that we're not aware of. It's just a shape problem that our silicon is underreporting. Look how much worse this one is. Silicon needs to come up, and it's not clear what else we can do to make that happen because I think it's just a fundamental difference in the powders that we're not able to refine for at this point. Okay. So let's close this one and do another example. So we can close this up, save it. And let's do another example. If we come over here to our examples folder, I'll just briefly do this one because I don't want to spend all day on it because there's a lot here that we could do. But we're going to go to this high temperature cobalt 304 example. This came from a paper that I worked on a while back. Find it real quick. Taylor Sparks, cobalt 304, where this one, I think, is it. Essentially, what we are interested in is we're looking at the transformation of a series of cobalt oxide powders as you heat them up. There's a lot of things that happen in this material. It's a spinel where the site occupancy changes. There's two different phases that are in competition. If you quench it rapidly versus slowly, you get different phases. So take a look here at this pattern. A couple things to point out here. When you take this cobalt oxide sample that we made and you quench it rapidly, you get one phase. You can see that there's 3 or 4 peaks here, and they line up with this cobalt oxide rock salt phase on the top, using this sort of stick pattern up here. Whereas if you cool it down really slowly, then you get peaks that just correspond to this spinel phase, cobalt 304, okay? And if you cool it down sort of in the middle, then you get some of both. So that's the first thing to note, is that how useful it is to do diffraction and actually show these types of stick figure plots so you can identify which phase is which. Or you could do that also just by putting like little symbols over each peak, but I think it's nice to do either or both even. I think that these histograms are a nice way to do it. So we'll talk about that tomorrow and how you generate figures like this really effortlessly once you're done with your refinements. Another thing to point out is look at the background difference for this one versus these other two. Something's going on there, and the difference is that on the first one, well, the first two, the upper two, I was using copper as our source. And copper has anomalous absorption for cobalt, right? So cobalt is absorbing that radiation from the K alpha 1, K alpha 2, it's absorbing those and then re-emitting it at a really high background. So that background's pretty gross. Then we switched it out when we did a slow cooling, and I put in a cobalt source for our radiation, and it doesn't absorb at all. Cobalt doesn't absorb cobalt. And so you get this really nice signal to noise. So that's a nice example of why you would want to do a better measurement. We should have gone back and actually remeasured these on the cobalt. I don't know why we didn't, but we didn't. But for the rest of the results in the paper, we were really careful about it. And so what you're going to have a chance to do is refine some of the same data that we measured carefully with cobalt source data to try and generate a plot like this. This is ultimately the result of doing a bunch of different refinements. We have some cobalt powders, cobalt oxide powders, that were heated to different temperatures, room temperature, 623, 800, 875, all the way up to some maximum temperature. And then we came back down again. And at each step in the process, we're going to monitor what's the phase fraction. It's 100% spinel if you cooled it slowly to start with. And then it'll switch to rock salt, and then it'll switch to there. In this scenario, you can look at what the lattice parameter is doing. In this column, you can see it's slowly increasing. That's what you expect to see. Most materials have thermal expansion. A select few actually do the opposite. They shrink. Here we're looking at the position of the atoms of the oxygen. You can see the weighted residual that I reported for these. So you want to be able to generate tables like this to report what's going on in your material. The reason why is because I've got it from here. Here's a figure from actual data. You know, doing this type of refinement, we were able to show that upon heating it, if you cool it down at an intermediate temperature, so there's a mixture of both phases, showing on the y-axis our weight fraction of, say, the spinel phase. It starts out about 2/3 spinel. As you heat it up, it will eventually convert to pure spinel, because thermodynamics, that's the more stable phase in this regime, and you've given it temperature and time to do so. But you do cross over a threshold at high enough temperatures where it switches to the rock salt phase, and upon cooling, that's a reversible transformation. And since we did it slowly at 5 degrees per minute, it now stays at the rock salt phase. This type of information about how phases change over time is is awesome, but you have to capture it by doing refelt refinement. So let's do just one example of that, because this one has some additional challenges that are worth showing you guys how to manage. So we're going to do a new example here. We're going to go back to we're going to open up a new file. So we're going to save project as, we're going to do a new project. Open new project right there. Do we want to save this? Sure, let's save our last one. Now we have a new project. So first thing we'll do is we were going to save this as, give it some name. We're going to move from the 9010 silicon example to this high temperature cobalt 304 folder. And let's just open this first one, this 25 degrees Celsius. That's our very first lowest temperature run. So we'll just type in test. If we wanted to put it in a subfolder for just the refinement, we could have. I guess I didn't this time. We're going to, just like before, we're going to bring in our powder data. It should be a Bruker raw file. And sure enough, there it is. That's the wrong one, actually. We have to go back to examples, cobalt 304, in the 25 degree C folder. There it is. I think this is a Bruker raw file. That's what we were using when we measured it. I was not able to read it. Let's try. Let's take a look and see what's in there. Let's try real quick and import powder data. So this GSAS powder data file, I think that also is sometimes a raw format. Let's try and read that one in. Yeah, okay. So that one, the GSAS powder format file, it can also read in RAWs sometimes. Again, this time we don't have an instrument parameter file. If you don't, then you would just hit cancel. In this case, we do have an instrument parameter file. So I want to show you how to read in one of those. In this case, we used cobalt radiation, right? Because the copper was giving too high of a fluorescent background. So we switched to cobalt. And it just so happens that I have two different instrument parameter files here, one for copper and one for cobalt, because I did it for both of those on that machine. So the data here was captured on a cobalt machine. So let's open that up, and it's going to bring in that data now. So there's the data that was run for that sample. This is the room temperature one. I think that had been cooled down sort of at an intermediate rate. We're now going to bring in the phases. I know because it was cooled down at an intermediate rate that there are two different phases present, and we should have the sieve cards for both of those. One is rock salt and one is spinel. So here's our two different phases. So we'll grab the rock salt phase first, bring it in, name it whatever you want, associate it with that powder pattern, and then we're going to bring in the other one, import phase from the sieve card. We're going to bring in the spinel phase this time. Again, you can name it whatever you want, associate it with that pattern, and we have our two available. So just like before, you could go to your instrument parameters. So right now it says copper right there, but if you look at these values, it says 1.789 and 1.792. Those are cobalt values. So even though it's saying copper here, that's not copper, it's cobalt, right? It's just the default value that it shows up as is copper. But if I move that to copper, I will not be able to fit this correctly because that's not the radiation source I used. I used cobalt. So that is currently set correctly. You'll notice that this came with U, V, and W's that were set. I also had refined this to find out what the zero was, and it was close enough to having no zero offset that I didn't adjust it. But these shape parameters were close enough, at least when I did the refinement, that this should be a decent starting point for the correct shape. We'll see if it actually is. And then just like before, you're going to refine a background. The background to me looks fairly flat. So 3 coefficients is probably more than enough. So we can do our first run here. And we will point out a few things from this. So, well, let's do one other run by turning on the lattice parameters of these and by turning on their individual phase fractions. Turning off the overall histogram on sample parameters. We're going to turn that off or just set it back down to 0 and then turn it off. And then we're going to refine it one more time. So this should give us at least a starting point for refinement. It's not going to be amazing yet, but it should be kind of close. Yeah, so let's take a look at this over here. If we come back over to our powder pattern, oops, drag that up somehow. I don't know how I did that. Let me rerun that. I'm not sure what's going on there. Okay, there we go. It's still, I'm not sure what's going on there. All right. Either way, it's just shifted that somehow, and I'm not sure how I did that. I will see if I can shift this down. See what I've done to do that. I'm not remembering how I've done that. No. What have I done there? All right, I'll look it up again and figure out how to do that. But what I wanted to show you was the fact that there's multiple phases accounted for, right? So there's these big peaks, and that's this blue tick mark coming from the rock salt phase. There's this phase right here, which is kind of by rock salt, but this one is unaccounted for. There's no green line because there's no expected Bragg diffraction there. So that's because I was using a sample holder right here. I've got them delineated. I was using a sample holder, which was diffracting. Part of it was being captured by the beam of the, the radiation. And so you would either need to add that as a third phase, which we could do, except I don't remember what the material was. We could try and search, peak match it and identify it. Or what you can do is you can just delete those peaks. You can tell the refinement, oh, I want you to ignore these peaks. And that's pretty common to do something like this. If there's a phase that was an impurity or something, and you don't want to, because you don't know what it is, but you know that it's not part of the refinement. If you want to refine the other components separately, then you would throw that out. Throwing it out will throw off your weight fraction if you don't capture all of them. In this case, I would have to go through and I'd have to turn off all of these regions, telling it to ignore them. So let's at least show you how you could do that if that's something that you wanted to do. I'm going to leave this up for a moment, and I'm going to go one by one through my pattern and show you how to add portions of the plot that you don't want to refine. You do that by coming over here to the limits under your powder background, right, under the powder file. Under limits, you're able to add limits for you to ignore or not. So right now, it has default a start and an end. It's starting at 16 degrees and it's going up to 100 degrees. But you can also add individual limits. So we're going to edit limits. We're going to add an excluded region. So you can do that by just plotting it, by clicking on this map, I think. So this first one right there, click on a point to be dragged. I have to how do you do this? It's been a minute since I've done it. Click on a point in the pattern to be excluded. So let's zoom in on this first one, because this first one comes from the sample holder. I'm going to click off my magnifying glass. And I didn't drag it, I just clicked. So it created a region, but it's not in the right spot, but that's okay. We can adjust that over here. So here's our first region. So because I didn't drag it, it just default put it from 19.7 to 19.8. But we want that to go out to say 20.5. That whole region can be excluded. So you can just modify it right there, 20.5. And now you'll see that that whole region is going to be excluded. When the least squares calculation takes place and it's comparing the actual data point to the simulated data point, it just won't use any of the data points in here in doing that calculation. Okay, so then we go back out and we could do that again for all of those ones if you wanted. So we could zoom in again right here on this guy. And then we come back over here to our limits and we could add another excluded region. And I turn off my magnifying glass and I'm going to drag it from here to there. No, I didn't drag. Oh, you can drag it right there like that. Okay. And now I've excluded that region as well. As you do this, you're going to want to be comparing to where the regions that you know are excluded. Maybe you got that by doing a search and match, or you could do it by just knowing which phases are supposed to be here or not, right? Because they have the tick marks or not. But this is allowing us to just turn those peaks right off. So when we refine this, again, let's drop out one more and I'll show you how it improves the refinement. Let's look at this one. We're going to turn that one off as well. Coming over to our limits column, we're going to add another excluded region. I'm going to zoom in on it so I can actually see it. And I'm going to exclude this region. There. Okay, we now have 3 excluded regions. You could continue this the exact same way, and you could continue to get rid of all of those, but that's sort of good enough to show you the principle. And then when you come back to refine this, again, our last refinement only got down to, it was already pretty good at 14.9%. It's going to get significantly better. Yeah, it's down to 12.7. And as you went one by one through these, it's just going to get better and better as you exclude those regions. So it's fairly common that you'll want to learn how to exclude regions using GSAS. To continue this refinement, to get it, correct the rest of the way, you would then want to make sure that the shape is being captured accurately. So I would zoom in on some of these most intense peaks and ask, yeah, they are too sharp right now, right? The actual peaks are much broader than that. So the actual ones are too sharp. Again, we got those shape parameters by refining a very coarse grain, something like lanthanum hexaboride, which tend to be really sharp peaks, but real samples might be smaller than that, depending on how you made that, or they might have some strain associated with them. So you'd want to update your instrument parameters, even though that these were set from running a standard and they give you a starting point, definitely doesn't mean you have to stick with them. You can for sure turn them on to make it better. So we could try refining that. We're going to see it's going to do much better. Yeah, it's matching that shape much more accurately now. Our error is going to be way lower. You look at our notebook, it's already down almost to acceptable range, but you can do better because we haven't even touched things like the atomic positions or the U isos. In this case, the atomic positions are actually very relevant. The oxygen position changes quite a bit in this structure. You can also refine occupancy. In this case, they're both the same item. They're both cobalt sitting on cobalt sites, so occupancy doesn't matter. But if this was another type of spinel, like, we did an example once where we did lithium manganese oxide, and the lithium usually sits on one side, manganese usually sits on the other, but it's possible to have different occupancies on this fractional occupancies. So you could actually introduce fractional occupancy as a refinement parameter. Or if you think that there's a good reason to believe that you have oxygen vacancies, then you can turn on the frequencies that and see if this goes down less than 1 to actually refine the amount of vacancies present. As before, anytime that you're looking at this crystal structure specific level information, you have to have good data. It will always refine, right? It's always going to run, but whether that's a meaningful observation or not depends on whether you have good data. Here we have our signal to noise ratios, almost 20,000 to, well, ish 15,000 to 0, which is pretty good. I would still prefer to have something like synchrotron data. I did turn it on and we talked about it in our paper, like what did we get from that and how does it relate to other measurements? Like we were able to calculate vacancies using a couple different ways. We looked at titration, we looked at neutron diffraction. And so by comparing 4 or 5 different ways of investigating whether or not those vacancies are present, you get a better picture than relying on any one of them alone. But that is how you would go about doing it in Rietveld refinement, is by refining that occupancy term. Okay. I think that's the main stuff I wanted to show you about this Cobalt 304 example. If you want to go through it, I have a whole video where I go through all of these and you can see how well your scores match up if you were to refine a whole bunch of these. One of the reasons why it's nice to do these ones is because you refined it once at 25C, you can then save that structure. Like when you're done with this refinement, you could come up here and you save it, save this project. When you open your next file, you can import it from the previous refinement. Like, so this 350C, right? If you start to do that refinement, if you make a new project there, you'd be able to come up there and you would be able to import your phases and your powder diffract. Well, you wouldn't want the powder, but you could import your phases from another experimental file. So you wouldn't have to bring them in from CivCard. You could bring them in both from there. Like if I do this and I go to some example, let's just do, even though we're not going to bring it from here. Let's say that I wanted to for a moment. Well, I had to save it as a GSP XP, which I didn't. But anyways, you can bring in those phases, which makes it a lot faster, and it saves the values, right? It saves the value of, say, like the lattice parameters, the atomic positions, and that becomes really important because let's just show you what happens if we try and do it without doing that, because I think this is a useful thing that might actually happen to you. So I'm going to close my GSAS for a moment. We're going to reopen it one more time, but we're going to do it at high temperatures and show you what's happened. So I'm going to come over here to GSAS, and we're going to just really quickly open up that one at 1,000 degrees. And then after this, I promise, we'll switch over to Vesta, and we'll talk about Vesta and plotting in our next class. But one last thing to cover here is Okay, so we're going to, we have a new project. Let's import powder data. We're going to bring in, I think this is GSAS powder data. We're going to go to this very highest temperature one at 1,000 degrees Celsius. Let's bring that in. Yes, we have to tell it which instrument parameter file to use. We want the cobalt one. Okay, so all of these things, remember, as you heat it up, the unit cells are increasing. So the pattern is shifting to the left. The pattern should be shifting to the left because the unit cells should be getting bigger. But if I bring in my phases from SIVCard that was measured at room temperature, maybe you can already see what the problem is going to be. I'm going to bring this in. I'm going to associate it with that powder diffraction pattern. I'm going to do the same thing with rock salt. So bring that phase in. There's rock salt associated with that pattern. Okay, I'm not going to turn on anything yet, but if I just try and run this, let's see what happens if I try and run a refill refinement. So it's wanting me to save this under some name, so we'll just do an example. Okay, give it a second, it's running it. And when we come back to it over here, okay, so I forget what's doing those X2s. Here we go. So let's zoom in on these because I want to show you that these are no longer lining up nicely. These peaks have shifted because it's gotten larger. This red phase, that's for a room temperature rock salt phase, is now no longer matching up with where the actual position is. Same thing over here. The room temperature spinel peak is right here, but the actual peak has shifted quite a bit because it's grown up. So if you try and actually tell it to put a phase there, it will make a mistake. So let's just manually set that and let me show you what happens. I'm going to manually increase it. I'm going to go to my instrument sample parameters. And instead of refining this, I'm just going to turn it up. It's currently set at 0.03. Let's just set that at 1. Well, it might need to be like 0.1. And I'll show you what I mean. So I'm manually moving all the calculated patterns to go up. And let me just show you what's going to go wrong here. That wasn't quite enough. Let me increase it just a little bit more so I can show you what's going on. We'll just go up to 1 actually. Okay, yeah, that's good enough to see. Okay, so I come back to my powder pattern, and when I zoom in on these regions, see, check it out. The predicted peak is right here, and it's not even close to the actual peak. So remember, the refelt refinement process, it's going to iteratively change the values of the lattice parameter if I turn on lattice parameter. But if it changes it and it makes it smaller, then it's going to move to the right. Right? And then it's going to not find that it's any better. So it might keep on going until it hits this one, which is the wrong peak altogether. If it by chance decided to go left, it might eventually find it. But you're guessing, you're hoping that it's going to choose the right way. And so this is a common thing where it will go wrong, it will diverge. Same thing with this peak. It's just so far off from its starting point that it can't refine the right structure. So this is an important part of refill refinement. That remember, you're always calculating a structure and then you're comparing that to the actual data. And if it's so far off at a starting point that it can't do a meaningful comparison, then the refinement process is not going to be able to find the correct structure. So what do you do if you're in this situation? Well, you can manually change things. We know that the lattice parameter needs to be bigger. So let's just try bumping it up a little bit. Let's imagine it goes up to like 8.3. It was at 8.1 basically. Let's increase it to 8.3. Same thing over here. It's at 4.26. Let's bring that up to like 4.5. You could do a quick back of the envelope calculation. Most ceramics have a thermal expansion parameter of something like 10 or so times 10 to the negative 6 ppm per K. So you could actually calculate it, or you just ballpark it, just try a few things and refine it and see if it gets close. Again, I'm not actually refining the unit cell yet. I'm just moving it by hand to see if I can get it close. And if we look at this, it's now I've overshot it a little bit, but check it out. It's starting to overlap a little bit. Because that's overlapping, if it moves it the wrong direction, the score would have gone down. And if it moved it the right direction, the score would go up. And if it goes the right direction, it will go down. So it should be able to learn it. Same thing over here. So I bet that we could turn it on right now, our refinement, and it would actually be able to find it. Whereas if we did it before, I don't think it would have found it. It's very possible it would have diverged. So let's try it out. Let's try hitting refine on these things and see if it actually moves to the right spot. We only did 3 cycles of refinement, which is not very many. Let's give it the typical 10 that I like to start with. Oh, I know the other problem. We have to turn off our, we're not letting it refine the histogram. It's set to a fixed value, which we don't want to do. So let's take this up to 10. And on our sample parameters, we actually have to turn on our scale factors. Well, we're going to leave that alone, but we're going to turn on our scale factors for the individual phases. So allow that to refine, allow for the cobalt, the individual phase fraction to refine. Now I think it will find the patterns. It might not, though. It's possible that it didn't find them. So if we zoom in on those, it didn't find them yet. So maybe we needed to move those over a little bit closer and try it again because it's still not finding them. We're turning on our phase fractions. So in this case, they were a little bit too big, I think. So let's make them a smidge smaller. Right? Let's go to like 4.4. This guy, go to like 8.2 and try running those. Once it gets close, it's able to do it the rest of the way. See right there, you can see it in real time, finding the right shape. At least for one of the phases, it found it. Yeah, for both of them, it found it. This was the impurity that we would have needed to cut out. These are the two. So now that it's able to find those, you could keep going and you could finish the refinement as normal after that. But I did want to point that out, that if you don't give it a decent starting point, because you downloaded a structure that was, say, measured under pressure or at temperature, and so the lattice parameter is just so far off, then that it's not overlapping, it will not necessarily find it. So you might have to actually adjust these numbers and get it to a close starting point. And after that point, it will be able to refine it. Okay. So let's say you did all this work and you did your refinements. Let's go back to our lanthanum hexaboride example. Actually, we can open a project. Fine. Let's go back to our lanthanum hexaboride one. So I'm going to go back to examples, lanthanum hexaboride, go to our refinement, wherever we left off. Let's say that you were refining some sort of material. This one we did a pretty good job on. And now you want to actually visualize the structure that you refined. We felt pretty good about this refinement maybe, so now you're ready to export the data. You can export the entire project as a CSV, as a sieve card. Let's do a sieve for a moment. So it says, okay, this reports the maximum shift ratio over all cycles, while the sieve expects it only over the last cycle. Oh, I see. So you have to tell it, like, do you want to set the maximum cycle to 1 and repeat the last? So it'll be same, sure. In other words, it doesn't want all the information from every cycle you ran. It just wants it from one final run, which is fine. So then it's able to export this. It's going to give you the opportunity to name it something. We'll just name it same thing, test.sieve. You can name it whatever you wanted. Right here it says, edit the instrument names. Note that a non-blank name is required for histograms. The sieve format, that's the crystallographic information file, has some requirements on how you name things. So you have to give it some sort of name. So like lab XRD, right? You have to name something about the instrument that was used. Ideally, you'd say the actual name of it, like it was a Rigaku, whatever, or a D8 Explorer, or an Expert High Score, whatever it was. It's expecting you, let's see, it says controls for phases. Here it's giving you the lanthanum and the boron radii and angles. Okay, that's fine. Check T and P values. It says temperature and pressure values appear to be defaulted. Are you sure that those are the correct values? This is important because remember, if your measurement was done at a high temperature, you really need to make sure you report that, because that will throw people off if they are trying to compare to that sample and your lattice parameter is way bigger. Well, that's because it was done at a high temperature. So it's saying, hey, you're using the default values. Are you sure that that's right? Yep, we are. Okay, so you go through this. It's asking you, you can go through and you can adjust things for all of this, or you can just create the sieve file. Give it a moment, it should create it. See if it did so. And there it is. There's our CIV file. If we open that up here, it's got all this information. So we didn't fill in the information about the author and the address and the email or the journal where this was published. You could have populated all that. It gave you the option to click those boxes and you could have filled them out, which we didn't do. But if you scroll down, eventually it'll get down to the actual structure. Here it is. So as for the actual structure, which is what most people care about here, okay, here's the lattice parameter that we got. Here's those values, the atomic positions. What was the thermal displacement parameters that we got? Again, this was that crazy one where they were negative values. But we create a CIV card, right? If you were trying to refine a structure and then you want to share that refined structure with somebody else, sharing the CIV card is the most common way to do that. Because then you can just take these things and you can open them with Vesta. Just to find it. No, did I open that one? Let's try that one more time. Let's go over here to our Vesta folder and try opening it from there. I'll just close this. We'll hang on to that for one more time. So I'm going to open my Vesta folder, scroll down to the Vesta app, and we can just open it directly from here. We're going to open. We're going to navigate to where that thing was, lanthanum hexaboride in the refinement folder, and open this guy. There it is. So it's able to open up this structure. Unfortunately, Vesta has some default colors, and in this instance, unusually, the default color for both lanthanum and boron is green. So they both look the same, but they're clearly not. So how do you use Vesta? Maybe before I dive into that, let me see a couple different questions showing up in the chat. So, okay, so I mean, when the powder pattern is not visible, how do you see it? Oh yeah, you just click once on that powder in the data tree. Like over here, if the powder pattern is not showing up, you can just click one time on this data tree, as opposed to the phases. If you click the data tree, it makes it show up. Somebody said, so we try to get a better fit, lower RW by playing around with the option. Is it like a logical estimate thing? Yeah, there's a sort of sequence that you start with. Like you want to start with the parameters that make the biggest difference first, like the lattice parameter, the scale, the shape of the instrument, right? And then as you're slowly refining those and you have confidence in those, then you turn on the more subtle things like the occupancies or the thermal displacement parameters. But that's, yeah, you're exactly right. There are a series of steps you go down in refining. Somebody says, the tips when we integrate these data refinement views, toggle switch views of the map, visual in 3D, are we switching software? Yeah, we're showing that right now how to do that. Once you have your refinement, all that information about the structure, how do you actually plot that in 3D? That's what we're going to do in Vesta. And then it says setups for switching views will be covered later. Yeah, we're going to talk about how to do that in a moment. Can you share the paper? Yeah, let me drop that paper in the chat. This came from here, that paper. If you wanted to follow along with what we did in that paper, you can see it there. Can you bring in the excluded area as well? Like if you accidentally exclude a region and you want to delete it, then you can. Is that the question? I'm not sure. You can, if you incorrectly excluded a region, you can just go to that region under your limits. Like if I come over here and I go to my limits, if I had added an excluded region and it was incorrect, like let me add a region, I guess, real quick. Over here, like I wanted to exclude that region. And for whatever reason, that was wrong. So when you came over here and now you've got that, well, you can just delete it and that will get rid of that region. Okay, if there's other questions, it's right here. Do you have a recommendation on the amount of RAM likely needed for GSAS? Ooh, that is a good question. And it does depend on a couple things. It depends on how much data you collected and how intense that data is. So for example, synchrotron data takes itty bitty tiny step sizes. So the total number of data points can be massive because it takes tiny step sizes. So those files are significantly bigger than your lab X-ray. Your lab X-ray does not have very many data points. Therefore, the RAM usage, just based off of data points alone, when you're calculating the difference, is going to be less. But there's other things to consider. Like right now on this plot, I'm showing you a cubic pattern. Lanthanum hexaboride is cubic. So there's not that many peaks. It's what we call a high symmetry structure. If you compare high symmetry versus low symmetry, like monoclinic XRD pattern, you'll notice that they have a ton of peaks compared to a higher symmetry one. Like here's one where it has lots and lots and lots of peaks. The more peaks that there are, you have to simulate a actual peak for all of those and compare it. And so the more there are, the more computationally expensive this gets. So if you are refining a monoclinic structure from synchrotron data and there's multiple phases and you're turning on lots of little individual things like fractional occupancy, thermal displacement, atomic positions for all of those, and there's many atoms in the potential unit cell, it can become really slow. That doesn't happen very often. I did hit it when I was doing synchrotron data for a few. Most of the time, you know, even if you're not working on like a workstation, if you're running this on a laptop, it's probably fine. But there will be instances where you might run into RAM issues, or at least it going very slow. But you could Google like what are the RAM expectations for GSAS? It might say like GSAS2 RAM requirements. I don't know if Brian Toby has listed that on his website or not. Let's see what he's got. GSAS2 RAM requirements limited only by the memory available compute used. Let's see if he's got anything on here about it. He would be the person to ask. By the way, the guy who developed this, Brian Toby, is extremely nice and responsive. If you ask questions like something like that, he would respond probably the same day. But I don't know offhand. That's a great question. Okay. So I'm going to close our felt refinement. I'll show you how to extract other information tomorrow from it, but for today, we're going to just close this one and let's say a few more words about Vesta before we're done today. So maybe the first thing you want to do with Vesta is like, you want to like see, we saw how to bring in a structure. We brought it in from a sieve card. There's other ways to do that, right? We can do a new structure. And you could just type it in directly. Like if you went to the literature and you went to like journal, solid state chemistry. And if you look at this journal, they publish a lot of structures, which are new structures. Let's go to like, I don't know, the latest issue and see if somebody is reporting a structure. See if we can find one there. Pretty common here. Structure, maybe this guy. So it's very common when you look in these things that it will have a table that simply describes the actual structure. Yeah, right here, for example. For this structure, it tells you what space group. It's giving you the lattice parameter. This isn't giving us the atomic positions. Ah, but here they are. So if you wanted to, you could take this data and you could create a structure in Vesta by hand using this data, right? So this guy, let's do it real quick because it's not too bad. So I would say, all right, I'm going to make a new structure. The unit cell is, you could come over here, you could look at, you'd be like, oh, it's number 225. So the space group, you could scroll all the way down to the space group number. It's cubic, number 225, right there. You could say that's my space group. Boom. You type in the lattice parameter, you pull that from the paper. This is for that LiCu2Ga. So up here, it said the formula for that. It was like 5.8843. So that's our lattice parameter, 5.8843. Okay. And then we go, I didn't quite finish that. Let's go to edit structure because I wasn't done doing that yet. Edit, data, unit cell data. We have to then add our 3 atoms. In the paper, it reports the atomic positions. You have lithium at the 4B site, half, half, half. So we could come over, we could add that. We could say add a new atom. We want it to be lithium. So select lithium. It's located at the half, half, half spot. So 1/2, 1/2, 1/2. By the way, notice that it adds the standard deviation, right? You could, if you knew the charge of it, you could give it there. You could give it some label. It's just called this lithium 1. Give it some label. If you knew the charge, it's probably +1, presumably, right? So now it's going to create those atoms at that site. You can see them all located. By giving it one single atom at a single position, symmetry, the fact that this is the 225 space group and it has those symmetry operators, moves and creates all the rest of those atoms. So then we'd add the other two. It's got copper at 8C located at quarter, quarter, quarter. So, okay, we can do another one. Let's do a new one. This one is copper. Locate, and you could give it whatever name you wanted, copper 1. It's probably +2. I'm just guessing. And it's located at quarter, quarter, quarter. So 0.25, 0.25, 0.25. Okay. That one, apply, and there's that one. And then lastly, we would add, this is gallium, 1 minus X gallium and aluminum. So this is a mixture. This is some amount of gallium and aluminum sharing a site, the 4A site located at 0, 0, 0. So now to add that one, we'd go to new. Let's add gallium first. We're going to say that gallium exists at, and we're going to give it whatever name we want, gallium 1, whatever its charge is, probably 3. These are all located at 0, 0, 0, but the occupancy now, like presumably the occupancy would be described in the paper, like maybe the occupancy is like 0.1 gallium and the rest is 90% aluminum. So we add that one. Now let's add the aluminum. So we're going to add aluminum right there, give it a name, give it a charge, give it an occupancy. Let's assume that it's 90% on the other one. I'm not exactly sure because I didn't read the paper, but you get the idea. And this allows you to create a structure by hand from scratch. If it's reported in the literature and it has this table that shows you these things, then you can report the structure, you can generate it yourself. And you see that it matches, right? Here's these structures, and that's basically what we're getting, okay? It's definitely easier just to open a Civ card, definitely, but you can do it by hand if you wanted to. Just a couple minutes left. You'll notice that in this one that we generated, there's no bonds. But in this one, by default, it's identified a bunch of bonds. So it does that by default doing some basic searches. If you come up here to bonds, edit bonds, it will by default find common bonds. Like it knows that by default, generally speaking, if you have a compound with boron and borons exist within a certain range of one another, then there's a bond. Like if they are found within 0 and 2 angstroms of one another, then that is a bond. And so it automatically found those. But if you don't think that that's a bond, you could delete that for one thing. Or maybe you think like, actually, the lanthanum is bonded to the boron. That's not true. But if you wanted to, you could add that. You could say, nope, I want to look for boron bonded to lanthanum and search out to maybe 3 angstroms and see what I find. That's not big enough. They're further apart than 3 angstroms because nothing showed up. So search out to 4 angstroms. Yeah, so there you go. Now, this is not real chemistry. It will create this structure, even though that's not really the bonding going on. In this lanthanum hexaboride system, borons are bonded to boron. It's not a typical anion-cation system. It's an intermetallic, right? So it's behaving differently. But that doesn't mean that you can't force it to create these bonds. But you might do so at your own peril because that's not a real bond. So we're going to say more about this next time. We're pretty much out of time on this. So next class, here's what we're going to cover. We are going to show you additional things to use in Vesta. We're going to show you more things that it's capable of doing. We started out in class today showing you that it can generate X-ray patterns, for example. So what else can it do? What's the best way to represent the structure that you refined? We'll do some examples of spinels, of clay materials, of some ionic conductors, a bunch of classic ceramics. We'll go through a bunch of those. And then the last thing we're going to show you how to do is take the diffraction data that you learned how to refine, export the actual files to make really good looking figures. That will all be covered next time. Are there any questions that we didn't that you didn't get a chance to ask yet that I can cover before we close today? Okay, if not, I am excited that we've covered this already. And tomorrow we will finish it up, show you a bunch more about how to make structures in Vesta look beautiful and useful. We'll do that for a bunch of relevant ceramic ones, and then how to make nice figures to go with it. So we'll see you all tomorrow.